Okay, hello everybody. Very happy to be here at this technical conference to present you this technology of Hummink, HPCAP, high precision capillary printing. And this is a brand new technology. The first IP for this technology was in 2018. And that was created by a very famous research institute in France called École Normale Supérieure. And this technology is based on atomic force microscopy, meaning that as in atomic force microscopy, you apply a frequency on a resonator and you continuously monitor this frequency. And with this frequency monitoring, you are able to position with very high precision your pipette that deliver the printing. Then that's unique. And that means that you have a perfect control of the printing. And during your printing, you continuously monitor the way you print. This is based on a natural force, which is capillary. You don't have to apply any pressure, any electrical field, which means that it's very easy to be used technology. Then this is an example here of this continuous monitoring that you have. If you have a slope on your substrate, if you have some high roughness, then continuously you are going to adjust your position of Z through, again, this frequency measurement and the variation of the frequency that you measure. And then like that, we can work with some slope. You have an example here of printing of a slope of 55 degrees. And you can adjust conformal printing also on high roughness in your system. Another thing that is unique, and it's linked to how this technology works, is the capability to create some bumps, some pillar with some very interesting applications that I will detail later on flip chip, for example. And the way it works here is that when you lift up the pipette, when you use ink that dry very fast, you are able to create such objects just by lifting your pipette and by the capillary that is created. And you can go to very high aspect ratio. I will show you an example of aspect ratio 20:1, and it's done in one step. Then the object is created like you see here. After that, we do a sintering, of course, for the electrical property, but it's a one-step process and you do the thing live. Then with this technology, you are able to do any kind of object, I would say, then bumps, dots, lines. You can do lines straight. You can go in different directions. And in terms of material, as it relies only on capillary, you don't have to put any electrical or any ultrasonic, then you can work with materials as different as metal, polymer, quantum dot, color ink, any kind of thing. And for the substrate also, the process window is very large. You can work with dielectric, plastic, conductive, semiconductor, then no limits in the things that you are going to do. The only limitation you will have will be on the size of the particle that you have in your ink, because as you will see, we print with very high resolution. If you use big particles, then you cannot print that on your device. Then you need to have the rule we have internally is that we use ink with particle size that are less than 10% of the opening of our pipette. That's what we do to avoid any clogging. The pipette is normal to the surface, which means that we can go to all the direction. You have some example here of what we can do. One of the applications we are working on, for example, is watchmaking to do some drawings. You have a tree on the left. You can see some circles. You can see some curves also. Then we do not have any limitation in the direction where we can go, which provide us a lot of different drawings that we can provide. You have to see this technology as a technology that is complementary. Then if we take the example of inkjet, we are not in competition with inkjet. We are complementary, meaning that inkjet can do things that we cannot do. And we can help the inkjet to go to other capabilities. And then I'm very proud to announce a partnership that we just signed with SUS Microtech. And the object of this partnership is exactly this one, to have complementary between the two technologies.